Hello, we're going to deal today with uh, particles and forces. And fields. So let's take a look at what's going on here. It's really an amazing saga. Okay, so here we go. We're going to be looking today at what makes up what we think of as the universe. And that means all the particles, all the fields, all the forces that go with it. Um, we've reached an impasse in 1975 when what was called the Standard Model was determined. And we have to extend the Standard Model to include new observations, new data. So let's take a look at what that might look like. The Standard Model is shown here as a bunch of particles on the outside and a bunch of fields on the inside. And they're actually all connected together by what's called a Lagrangian due to Lagrange. Lagrange reformulated what Newton did and showed that everything worked with a path of least action, and the action is defined by this Lagrangian that's shown here. So the Standard Model encompasses this Lagrangian here. So it's more than just a picture. There's a whole series of equations that go with this. So let's dig into it. This all came about from a comment by Richard Feynman, the Nobel laureate in physics, who he said, what if all scientific knowledge were to be destroyed, save for one sentence? What is the one statement that would contain the most information in the fewest words? And he believed it was that all things are made up of atoms, little particles that move around in perpetual motion, attracting each other when they're a little distance apart, but repelling upon being squeezed into one another. And so that's really what we'll be dealing with here is the notion of atoms. The Standard Model we talked about shows that atoms, in fact, are made up of other components, but that doesn't take anything away from the atom. We've got an outline here for what we're going to cover, you can see. And we've got a picture here showing what an atom might conceptually look like. It shows a core nucleus consisting of protons and neutrons, and then there's a cloud of electrons running around it. And that picture still appears to be valid no matter what we do for matter, and we'll see how we have to extend it to encompass other things. Where in the world did this notion of atoms come from? It came from apparently a Greek named Democritus around 400 BC. We have no idea how he came up with this, but he said that all matter is made up of fundamental entities called atoms. Atoms are discrete. They form the smallest unit of matter, and matter can only be divided down to atoms. So if I took something like flour, for example, and I tried to cut it up and smash the pieces of flour and got things finer and finer, I could only go all the way down to where I would hit the atoms that made up what goes into flour. I couldn't go any further than that. There's no way to have a fraction of an atom. So the smallest and indivisible bodies that are called atoms, they're too small, he believed, to be detected by our senses, but they're huge in numbers, and they come in all kinds of varieties. They've existed forever, and these atoms are in constant motion. Everything that we see around us today is made up of aggregations of atoms, and they're brought together by collisions of different sorts. There's all kinds of interactions that occur. But for Democritus, the only true reality is the atoms and the void in between atoms. So what we think of as earth, air, water, fire, plants, humans are merely combinations of atoms and the void. These are really the fundamental things that encompass everything. We have to go a long way from when Democritus did his pronunciations in 400 BC, clear up to almost 1800, the period of 2200 years. Antoine Lavoisier defined an element which scientists couldn't decompose into simpler substances by experimentation, and that substance he called an element. And so John Dalton thereafter studied data that he'd gathered, and he noticed that there was a thing that occurred here. In compounds, for example, which contain two particular elements, the amount of element A and the amount of element B always seem to differ by ratios of small whole numbers. An example of this is water, which we now know is made up of, we have a chemical formula for it, H2O. So we have two hydrogen atoms and one oxygen atom, and therefore the ratio is two hydrogens for every oxygen. So let's see where that takes us. An Italian, Avogadro, proposed, and this is really fundamental to everything, that equal volumes of any two gases at the same temperature and pressure contain equal numbers of molecules. So in other words, the mass of the gaseous particles doesn't affect the volume that it occupies. This is a very fundamental observation or hypothesis. It provided a method for deducing the relative weights of molecules of gaseous elements, because the relative gas densities would directly indicate the relative weights of the particles that made up the gases. And this led to a second hypothesis that the particles of certain elemental gases were pairs of atoms. So for example, we don't see oxygen, but we see O2, pairs of oxygen atoms. We don't see hydrogen, we see H2. Hydrogen as a gas is two hydrogen atoms. And then when we react these things together, it's possible for these things to split. And that's how we get that 2 liters of hydrogen will react with 1 liter of oxygen to produce 2 liters of water vapor at a constant pressure and temperature, which suggests that the single oxygen atom split in two in order to do this. Now, moving forward another 20 years, we see that we came across a notion of isomers or isomerism. And this notion here is that we had substances with the same chemical content, but they had different properties, so they're isometric to one another. So, for example, silver fulminate and silver cyanate both have 107 parts of silver, 12 parts of carbon, 14 parts of nitrogen, and 16 parts of oxygen. And their chemical formulas are the same, but there's something different about these two things when you actually look at them. So Louis Pasteur hypothesized that these molecules of isomers might have the same set of atoms, but they might be arranged or interconnected differently. That's in fact what happened, what we now agree. In 1874, Hoof proposed that carbon atom bonds to other atoms occurred in a tetrahedral arrangement. There were 4 bonds for every carbon atom. And working from this, he was able to explain the structures of organic molecules that could predict how many isomers a compound could have. So in the picture here, we've got pentane, which is C5H12, 5 carbon atoms and 12 hydrogen atoms. And Van Hoff showed that there are 3 possible configurations for pentane, and we show all 3 of them here, 1, 2, 3, and there are no more. So this leads us up to Mendeleev. Mendeleev was known for formulating what's called a periodic law and creating a periodic table of elements. He noticed when he arranged the elements in a row according to their atomic weights, there was a certain periodicity to them. So for example, the second element, lithium, had similar properties to the 9th element, sodium, and the 16th element, potassium. a period of 7. And similarly, beryllium, magnesium, and calcium were similar, and they were 7 places apart from one another. So using these patterns, Mendeleev predicted the existence and properties of new elements, which is a real test: scandium, gallium, and germanium. And the periodic table could predict how many atoms of other elements that an atom could bond with. For example, germanium and carbon are in the same group in the table, so that their atoms both combine with 2 oxygen atoms each. We can have germanium oxide and carbon dioxide. And he found that these patterns validated the atomic theory because it showed that elements could be characterized by their atomic weight. We now know that the atomic weight is the number of protons that's in each nucleus plus the number of neutrons. But the number of protons concerns the actual charge. The number of electrons has to equal the number of protons. So it is not arbitrary. You can't simply stick something in somewhere and see what happens. Notice that he used the notion of 7. He didn't realize that the inert gases, helium, argon, etc., were there, and that actually gave him 8, not 7, for one of the rows in the periodic table. Building on this, we had the notion that we had gases, and that the gases are made up of molecules, and they bounced against one another, the molecules, and their bouncing created temperature, and it created pressure. And so if you draw on this, the physicist Daniel Bernoulli, and he's also a mathematician, postulated that the pressure of gases and heat were both caused by the underlying motion of molecules. And in 1860, Maxwell, who was a very vocal proponent of atomism, used this to derive what is now called statistical mechanics. And these are fundamental relations between temperature, pressure, and volume, and heat capacities of different sorts that are still true today. They're taught everywhere. This was picked up on by 2 Viennese, Ludwig Boltzmann and Rudolf Clausius, who expanded on this work, and in particular, the notion of the first law, thermodynamics, or statistical mechanics, which is conservation of energy, and the second law, which is related to entropy. Then in the 1870s at Yale, Josiah Willard Gibbs extended the laws of entropy and thermodynamics, and he actually coined the term statistical mechanics. Most of his work was ignored, although it was incredibly fundamental. In the 1900s, Einstein wrote a paper on statistical mechanics, not knowing that Gibbs had work. He went back and looked at what Gibbs did, and he said he would have never written up and published what he had if he'd known about what Gibbs had done, which gives you some idea of what Gibbs was capable of doing. Now we follow a different path here, related to statistical mechanics. In 1827, the British botanist Robert Brown observed that dust particles inside pollen grains floating in water constantly jiggled about for no apparent reason. So in 1905, Einstein theorized that this Brownian motion was caused by the water molecules continually knocking the grains around, and developed a mathematical model to describe it. And this model was validated experimentally in 1908 by Jean Perrine, who used Einstein's equations to measure the size of atoms, and actually was quite close to what we realize they are today. So now we're getting more and more activity in what an atom is. Atoms, again, were thought to be the smallest possible division of matter until 1897, when J.J. Thomson discovered the electron, which turns out to make up parts of the matter atoms. So he ended up with a model which was popularly known as a plum pudding model of the atom, based on the idea that the electrons are distributed throughout the sphere of positive charge, having the same density as raisins in a plum pudding. Thomson likened it to a liquid, and he proposed that the electrons moved around in patterns governed by electrostatic forces. But he never once called it plum pudding. That was due to popularists. And so in 1906, Millikan and Harvey Fletcher performed an oil drop experiment where they measured the charge of an electron and determined it to be the fundamental unit of -1. Electrons were chosen to be negatively charged, protons positively charged. And since the hydrogen ion and the electron were known to be indivisible, the hydrogen atom is neutral in charge. The positive charge in the hydrogen was equal to this value of +1. I actually did this oil drop experiment as an undergrad to actually measure this charge on an electron. Now, in 1911, one of Thomson's students, Ernst Rutherford, discovered that the positive charge in most of the mass of the atom is concentrated in a very small fraction of its volume. So what he did was he took what he called alpha particles. They're actually nuclei of helium, and he shot them at a foil that he had. And so here we have a picture showing Thomson's model with the electrons in blue here and the positive charge in pink. And if he shot these things, he expected they'd go right through. There's nothing there to really stop it. But what he actually observed was that several of these things not only didn't go through, they bounced back at huge angles. This one here looks like it's bouncing back at over 140 degrees from the direction that it came in at. And here's another one that's just deflected down by, say 30 degrees. So you can see that while these might be rare, that they did occur, and that suggested that the atom that you're dealing with as the positive charge is in the very small nucleus, and the nucleus has most of the atom's mass, and the charge is running around it in a fog. One way to put this in perspective is that if we looked at a typical atom and the nucleus was the size of a chalice in St. Peter's in the Vatican, that the electron cloud would be forming the whole basilica of St. Peter's. So you can see that there's a very small nucleus relative to what makes up the size of an atom. We take the electron to be confirming the size. Now, there's several problems with this model. The first is that unlike planets orbiting a sun, the electrons are charged, and so any accelerating, and you are accelerating because you're rotating around a nucleus, the accelerated electric charge will emit electromagnetic waves, and if it does that, then it loses energy. In fact, it'll lose energy and spiral in toward the nucleus and collide with the nucleus in just a small fraction of a second. So this isn't too good. And the second problem was that the planetary model couldn't explain how there were these highly peaked emission and absorption spectra of atoms. When you shot energy at it, you either got things absorbed or emitted, but they occurred in unique bands, spectra that were unique to that particular atom or that particular material. So in 1913, Niels Bohr incorporated this idea that an electron could only orbit the nucleus, in particular circular orbits with fixed angular momentum and energy, and its distance from the nucleus was proportional to its energy. So under this model, an electron could not spiral in the nucleus by definition. It was simply in a fixed orbit. And the leaps between these orbits defined the fixed energy levels that you saw when you had light emitted or light absorbed. An electron hopped uh, from one energy level to another. And so it goes. So this was truly radical. In 1913, the radiochemist Frederick Soddy discovered that there appeared to be more than one variety of some of these elements, and he coined the term isotope. Actually, it came from Margaret Todd. So an isotope actually was originally discovered by Annie Besant and Charles Leadbeater through observations that they made in intense meditation in 1894 onward, and they were published in 1908. In the same year, J.J. Thomson conducted an experiment where he channeled a stream of neon ions through magnetic and electric fields, striking a photographic plate at the other end, and he observed that there were two glowing patches on the plate, which suggested two different deflection trajectories. So he concluded some of the neon ions had a different mass, and the nature of this differing mass would be explained by the discovery of neutrons in 1932. All atoms of the same element contain the same number of protons. Different isotopes have different number of neutrons. When we go back to 1815, William Prout observed that the atomic weights of the known elements were multiples of the hydrogen atomic weight. So he hypothesized that all atoms are agglomerations of hydrogen, and the problem that they came up with was that this didn't seem to match the data, except that when you have this notion of isotopes, then his observation attracted new interest. And in 1898, Thomson found that the positive charge of a hydrogen ion equaled the negative charge of a single electron that he discovered. And so that suggested that in 1911, Rutherford, with his work here, led to other work in 1911 by the Dutch physicist Van den Broek, who noted that each successive chemical element increased in atomic weight by an average of 2, which in turn suggested that each successive element's nuclear charge increased by 1. Well, if that's the case, then Moseley carried out some X-ray emissions, all of these elements on the periodic table, found out that the frequency of the X-ray emissions was a mathematical function of the element's atomic number and the charge of a hydrogen nucleus. And this in turn led Rutherford to bombard nitrogen gas with alpha particles, and he observed hydrogen ions being emitted from the gas. So he concluded the alpha particle struck the nucleus of the nitrogen atoms and split off these hydrogen ions or protons. So the net of this was Rutherford concluded that the hydrogen nucleus was a single particle, a proton with a positive charge equal to electrons, a negative charge. And the term proton was suggested to cover this. And all atomic nuclei contain a number of protons equal to the atomic number. The atomic number is different than the atomic weight, but it does determine the element's position in the periodic table of elements. So we're making real progress here. In the 1920s, physicists believed the atomic nucleus contained protons plus a number of nuclear electrons that reduced the overall charge. These nuclear electrons were distinct from the electrons that orbited the nucleus. This was false because the atomic numbers of the elements were less than their atomic weights, and radioactive elements emit electrons in the process of nuclear decay. So Rutherford hypothesized a proton and electron could not bind together into a nuclear neutral doublet. In fact, what happens with a neutron is when it decays, after about 10 minutes, if it's left in free space, you'll get a neutron will decay into a proton and electron. and a neutrino, a small itty-bitty neutrally charged particle, a neutrino. So this led Walter Brophy to observe that the beryllium emitted highly penetrating electrical neutral radiation, and this could knock off hydrogen atoms out of paraffin wax. But Chadwick found that this ionization effect was too strong to be due to electromagnetic radiation. And so Chadwick went ahead and exposed various elements such as hydrogen and nitrogen to the mysterious beryllium radiation, measured the energies, and deduced that the radiation was actually composed of electrically neutral particles, which couldn't be massless, but instead had to have a mass comparable to the proton. And this is what he called the neutron. Neutrons, as we said, are not simply a proton and electron. They include this other neutrino as well. So now things get really interesting. Louis de Broglie was awarded the Nobel Prize in Physics in 1925. He claimed that all particles have wave-like properties, and all waves have particle-like properties. So what you think of as a particle is actually partially a wave. What you think of a wave is partially a particle, which is highly confusing. But that led to being sorted out in what is now called quantum field theory, which views particles as concentrations of resonating energy. Ron Cowen in the 1990s confirmed this when he went into deep meditation and observed an electron, which is shown here. So there's a picture of an electron, and you'll see that the electron actually consists of 10 closed strings that are resonating violently, and they capture energy in here as they resonate here. This is actually forms a torus. There's a hole in the middle, as you can see here. And the other thing about this that Ron discovered was the electron is coated with blocks of information. The blocks of information are constantly scanning the world around us, and governing how controlling how the electron is going to resonate and keep this energy. And this is coding not simply the electron, but the walls of quantized space compartments, which is everywhere. Ron also observed that there was something called dark matter, we'll come to in a second, and that they didn't have 10 strings, they had 5 closed strings, and they had no charge whatsoever. Here, this is an electron, this has a charge to it, and we'll see as we go on, the other things have charge. So this takes us up to the standard model that physics arrived at in 1975 timeframe. So it includes things called quarks that are shown up here, and you need 3 quarks to make up a proton or a neutron. The different types of quarks. What Ron Cowen observed was that each of the 3 quarks is made up of 3 subquarks that have a fraction of the charge that each of these quarks has. So the subquarks are really the fundamental thing, not the quarks. Then we have things called leptons, where we have an electron that has a couple of things that are actually resonant states. The electron resonates and can go into 1 or 2 other energy states. And what comes with this is a neutrino that has an association with the electron, and that can resonate into 2 other states. So here are everything that we call particles sitting here. And then finally, we have the forces that physics has discovered. The photon, which is tied to electromagnetism, for electricity and magnetism. And then the gluon that's tied to the strong force. In the nuclei, we have positive charges next to one another. Normally, these would repulse one another, but when they get close enough together, they attract one another. And that's viewed as this gluon. And then finally, we have these other things, the Z and the W boson. Actually, all of these arise out of the photon. The photon is the fundamental thing, and all of these arise out of electromagnetic theory. So there's a series of fields here that we just talked about, all due to electromagnetism. And then we have something that's a scalar called the Higgs boson. And this shows up at the start of the universe when it actually goes from zero to something non-zero. And that determines the masses, the relative masses of all of these different particles here throughout the entire universe. So this Higgs boson is everywhere in the universe and governs everything. And that leads us in turn to various things that occurred. Finding the Higgs boson took till 2012, even though it was predicted in 1964, which gives you some idea of how difficult it is to go find any of these things. So one of the things we'll come up with here in a standard model is a summary. Here we've got all the particles on the outside, the fields on the inside. And so we have, according to this picture here, 12 elementary fermions that consist of 6 quarks in any quarks and 6 leptons in any leptons that give us a total of 12. And 5 elementary bosons, the gauge bosons that are all here shown in orange, and the Higgs boson shown in the center. And so this Lagrangian for the standard model encompasses all of these things. And all of these are energies that are localized to create these particles. Basically, what got missed was what's called dark matter and dark energy. And this is not a minor miss. After 500 years of active investigation, starting with people like Galileo, Tycho Brahe, Copernicus, in building better and better telescopes, it's determined that modern science has been studying 5% of the mass and energy in the universe, the remaining 95% called dark. 27% is called dark matter, and 68% is called dark energy. So let's look at each of these in turn. In the 1920s, Fritz Zwicky at Caltech observed there were many galaxies out there. They appeared to be spirals of stars. So if the stars attract one another by gravitation, and they're all spinning around a center of mass for the galaxy, and they have an average mass for each star, then he realized that based on what he saw, these galaxies would all fly apart unless there were a lot more hidden or dark matter to provide the necessary gravitational attraction. We now estimate that to be 27% of the universe. So in other words, it's more than 5 times what we call matter or energy. Not a minor miss. In the 1920 timeframe, Edwin Hubble at Caltech observed that all the galaxies are moving away from one another, and the force driving this repulsion is called dark energy. This makes up 68% of the mass and energy in the universe that we're in. And so how in the world any sort of standard model is going to have to incorporate dark matter and dark energy? How in the world do we do this? So we come up with a model here that has actually the geometry for the universe is critical here. It has 26 real dimensions to it, 24 spatial and 2 are time. But yes, there's 2 time dimensions. So the thing that we call matter resides in a 10-dimensional subspace. There's 4 dimensions for time, 3 for space and 1 for time, which we call space-time. And then there's 6 what are called compactified dimensions. These compactified dimensions are wrapped around the different directions that we see here in space, and they're such that the scale for them is incredibly small. We haven't been able to develop instruments yet that allow us to see them, but we were able to see that due to Ron Cowen, that in fact there are 3 holes associated with this in the 6-dimensional compactified space. So if we go back here to this picture, we see here we have the electron, and then two resonant modes for the electron. Those other resonant modes, for a total of 3 modes, is due to the fact we have 3 holes in these compactified spaces. Similarly, for the electron neutrino, we have 2 other resonant modes, so a total of 3. These are all due to the resonance of those holes that occurred there.
Don't you have a caveat?
Yeah, I do. Then we have dark matter, which is in a 10-dimensional subspace directly next to us, or orthogonal to us, that has its own 4 dimensions for space and time, and it has a 6-dimensional compactified dimensions, just like the matter dimensions do. This one, though, has 4 holes. Another thing about this is this only contains, as Ron Cowen observed, this only contains one type of particle. There's 5 closed strings that resonate, and they can resonate into because of their 4 holes being here, into 4 different modes. But there's no charge associated with this, unlike over here in space-time and with matter, where we have positive and negative charges. There is no electromagnetism here. So the dark matter, while it's very dense, it's you should think of it as nuclear. It's made up of subquarks that are made up of these 5-string resonances that capture globules of energy. The net of it is that these are, remember how we describe the electron and the nucleus, is the electron is so much further out, a couple thousand factors out from the size of the nucleus. The same thing's true for the subquarks here for dark matter. So this can be scattered all over the place, and yet it'll take up actually very little space, quote unquote, in the 10 dimensions that it's working in. And then finally, there's a synchronizing set of compactified dimensions that connect to these. So we have 6 compactified dimensions with 3 holes for matter, 6 compactified dimensions with 4 holes for dark matter, and then the higher realm, if you will, where we have 6 dimensions with 8 holes. Well, if there's 8 holes and there's 18 dimensions here, 3 times 6 is 18, then there's really only 10 dimensions here that make this up, and that matches what we find the mystics, the Kabbalists saw in the Tree of Life was 10 Sephiroths, 10 actual planes that make up the universe. So when we go back and try and summarize all this here, plus we touched on the notion of information that coordinates, that controls everything, and apparently is using these other compactified dimensions to send signals around, controlling everything. We end up with a complete new standard model to encompass everything. We have matter, which has not 24 fermions in it here, with 18 10 string closed quarks and subquarks are the real basic units here. And then we have these leptons and antileptons. We have elementary matter bosons, but now the gauge bosons are multiplied by, there's actually only 3 of these. There's the gauge bosons and the Higgs boson here. And then we have the elementary dark particles, which make up 4. It's not shown here because we haven't included it. And then we have compartments of space, and those can each hold up to 2 subquarks. So that makes up everything here, and that requires a new Lagrangian. That's it. Voila. Have a good, and we will see you later.